Hello. So let us start with the question 49 of second chapter of Zettili. So we are given a Hamiltonian of two-state system, and along with that we are told that phi 1 and phi 2 form the complete and orthonormal basis, and E is a real constant having the dimensions of energy. So basically when we operate Hamiltonian on some wave function, we will get eigenvalue, that is an energy eigenvalue, since it is given that E is in the terms of energy. So the first question we have to calculate that to see if H is Hermitian, and if so, calculate the trace of H. Alright. And in the second question, we have to find the matrix in the basis phi 1, phi 2, and see how the matrix look. And once the matrix is formed, we have to see what are the eigenvalues and the corresponding eigenvectors. Also, we have to calculate the trace of that matrix which we have formed, and we have to compare that value with the result obtained in the first part. Alright. And at the end, we have to calculate certain commutators. So calculation of certain commutators, I will refrain from going to that particular section because that's quite easy to work upon and go ahead with that. Okay, so first let us start with the first question to see if the H is Hermitian. So one thing we should know, that if we take a dagger of phi 1, we will get phi 1 ket, we will get bra phi 1, and same goes for ket phi 2. Okay, and since they are orthonormal, phi 1 is equal to 1, phi 1 phi 2 is equal to it's equal to 0, and we have to E belongs to real. Now to see if H is Hermitian, so we have to see, we will first calculate H dagger, that is E phi 1 minus phi 2 minus I phi 1 phi 2 plus I phi 2 phi 1. Now applying dagger to the whole bracket, we get E dagger into dagger of each of these quantities. And once we calculate those daggers, I am refraining from going into each step, calculation of each step. So I will directly write the result over here that we will get from the dagger, and phi 1 minus phi 2. Let me use some other ink. Now in this, the positions of phi 1 and phi 2 will change, and this I will be replaced by minus I, and minus will get plus. So we get plus phi 2 phi 1. Okay, and same goes for this. This will be replaced by minus I. So minus I phi 1 phi 2. Okay. Now we see that E is a real number, so E dagger is nothing but E. Now we see that this equation that we have obtained over here is nothing but similar to H, which is given in the question. So this is equal to H. We say that H dagger is equal to H, which implies the Hamiltonian is Hermitian. Alright. Now we have to calculate the trace of this operator. Now the trace of the definition for the definition of h cap is nothing but summation phi n h phi n, that is phi 1 h phi 1 plus phi 2 h phi 2. Now I'll put the values of h operator over here and phi 1 phi 1 phi 2 minus I phi 1 phi 2 plus I phi 2 phi 1 into phi 1, and similarly we go for h phi 2. Okay, and from this, the when phi 1 is multiplied by phi 1 over here, we get 1. And if we just simplify this particular thing, we are reduced with e plus phi 2 h phi 2 e minus e 0. So the trace of that operator is 0. Okay, I would highly recommend you to please work out these simple steps where you have to operate, we have to like expand these bases. Now coming to question 2, we have to make the matrix out of the given operator. So if hij is the element of this matrix, then hij is defined by h I h and j. So h will be a 2x2 matrix. So it's phi 1 h phi 1 phi 1 h phi 2 phi 2 h phi 1 phi 2 h phi 2. I would recommend you to please go out and do every single step so that it is very useful for you to understand how things come up. And since this is a very basic calculation in terms of quantum mechanics, so I will try to refrain going from the calculations, and we get I minus I minus 1. Okay, so we have calculated the matrix that is representing H. Now we have to calculate the value of this matrix H. So first we will form a characteristic equation for the matrix. So this is the characteristic equation, and we get E. Over here it's identity, not an energy one, so this one is identity. Determinant of H minus lambda E, so H is E one minus I minus 1 minus lambda 0 0 1. We have to calculate the determinant of this, that is E minus lambda minus IE plus IE minus E minus lambda, which is equal to 0. So we are having E minus lambda minus E minus lambda minus IE minus IE equals to 0. This one will get cancelled. Minus E minus lambda, E plus lambda minus E square equals to 0 minus E square minus lambda square minus E square equals to 0. Lambda square equals to 2E square, which implies lambda equals to plus minus root 2E. So these are the eigenvalues, and we can see that the eigenvalues are real, and we need to find the eigenvectors of this matrix. For lambda equals to root 2E, H minus lambda E into the eigenvector H1 equals to 0. E 1 minus I minus 1 minus E 1 minus root 2 minus I minus 1 minus root 2 H1 2. So these are nothing but the column vector of the eigenvector that we have already. So we can just remove this, as we can shift this to the right hand side and just cancel it. And now we get two equations, 1 by root 2 H11 plus minus I H12 and I H11 plus minus 1 minus root 2 H12. Okay, both are equal to 0. Now if we see that these both equations are similar, in the sense that if you just work on the, if you like multiply I in the first equation and divide the first equation by 1, multiply and divide the first equation by 1 plus root 2, we will get nothing but the second equation. So we can say that IH11 plus IH11 is equal to 1 plus root 2 H12. So if we have H12 as 1, we can just take a random number H12 as 1, H12 as 1, then our H11 will become minus I 1 plus root 2. Okay, and similarly we'll find the eigenvector for lambda equals to minus root 2E, that is E1 plus root 2 minus I minus 1 plus root 2. Now the eigenvector is H2. So H21, H2 2 equals to 0. Now 1 plus root 2 H21 minus I H22 equals to 0. Alright, now I h2 1 minus 1 plus root 2 h2 2. Again, these two equations are similar, so instead of working on both the equation, we'll just take the first one and work our way out. So h2 will be, if we take our h1 as 1, then our h22 will become minus I1 plus root 2. So our h1 is minus I1 plus root 2 and 1. Our h2, the second eigenvector, is 1 minus I1 plus root 2. Alright, so we have got the eigenvalues and eigenvectors for this. Eigenvalues are done, eigenvectors are done. Now what we are left is to calculate the trace of the matrix. So to calculate the trace of the matrix, I will have to write the matrix again. So the matrix H is E 1 minus I plus I minus 1. So trace is E minus E. In the matrix form, the trace is nothing but the addition of diagonal elements. So trace is 0. So trace of H matrix is 0. Trace of H operator is 0. So the trace of operator and matrix are same. So let us conclude that trace of H cap is equal to trace of H matrix. I am just using a double dash under the H to represent that it's a matrix. It's not any general convention, but yeah, we can surely use that. So I guess we are done with the two questions, and the last one is quite simple. Calculating the commutator, we have done it quite a number of times, so that won't be a big issue. So I hope you find this quite pretty useful. This question was really good to work with, and the really good part was how to form the matrix out of an operator. This is one of the really insightful thing to work on. So thank you for watching the video.